In today's lecture, we are going to see the concept of a very important tensor which is vividly used in the discussion of general relativity. Actually, this was the tensor which compelled Einstein to think that gravity is not a force but it is just the curvature of space-time. So this is a very important tensor to deal with the problem of general relativity. So what is this fellow? In fact, I am talking about the Riemann Christoffel tensor, or you may simply say Riemann tensor, and it is popularly known as curvature tensor. Okay. So in fact, this curvature tensor, which is also known as Riemann Christoffel tensor or simply the Riemann tensor, this is actually a central mathematical object in differential geometry and general relativity. Okay, as I have told you. In fact, this tensor encodes the intrinsic curvature of a manifold and describes how vectors are twisted or rotated as they are parallel transported around infinitesimal loops. It is foundational to the understanding of space-time in general relativity, as I have told you. In fact, this tensor connects geometry to physics, and this connection between geometry and physics allows Einstein to describe how the gravity is not just a force but it is just the curvature of space-time. It means due to the curvature of space-time, gravity arises. And this is actually shaped by energy and momentum. Okay. So how the concept of this Riemann Christoffel tensor arise and what are its physical interpretation and what are its important properties, we will learn in this lecture, and its use will be seen when we will discuss the Einstein theory of general relativity. In fact, you have learnt earlier that the covariant derivatives of fundamental tensors, all the three fundamental tensors, that is the covariant fundamental tensors G mu nu, the contravariant fundamental tensor G mu nu, and the mixed fundamental tensor G mu nu. This, this G mu nu, which is mixed fundamental tensor, is also denoted by this symbol delta mu nu. And we have seen in my previous video that the covariant derivatives of all these three fundamental tensors are 0. Okay. So you can say that when we differentiate, we take the covariant derivative of G mu nu or the contravariant fundamental tensor G mu nu or the mixed fundamental tensor G mu nu with respect to the coordinate xl, then it is 0. Okay. What is the physical meaning of this result? Actually, this result implies that there is no tensor of rank 3 which can be obtained entirely from the fundamental tensors and their covariant derivatives. You can't obtain a tensor of rank 3 by the covariant derivative of by taking the covariant derivative of these fundamental tensors. But you will get surprised that there are two very important tensors. First one is of rank 2, which is denoted by the symbol this R mu nu. This is actually called Ricci tensor. In fact, our forthcoming video we will discuss this Ricci tensor in very detail. It is also a very important tensor to discuss the general relativity. Okay. And another tensor which is of rank 4, that is denoted by this symbol R, contravariant index lambda and covariant indices mu nu sigma. This symbol actually is for the curvature tensor, or you can say the Riemann tensor. In fact, when we will see the concept of this Ricci tensor or curvature tensor. In fact, in this lecture we are going to see the concept of curvature tensor only. Then you will see in the final result for the expression which defines this curvature tensor, you will see that the expression defining this curvature tensor involves only the first partial derivative of the metric tensor, okay, and the Christoffel symbol, which ultimately depends on the metric tensor or fundamental tensor, okay, and these are obtained from a repeated process of covariant differentiation. So this result where you see that the covariant derivative of the fundamental tensors is 0, this actually implies that we cannot have a tensor of rank 3, okay, uh, but we may have a tensor of rank 2 and a tensor of rank 4 by the repeated covariant differentiation, okay. So this was a short, or you can say brief introduction regarding this Riemann tensor. Now we are going to see how we can define this Riemann tensor, okay. I am not just writing its definition or directly its expression, but we will derive it, okay. So let us see the derivation for this curvature tensor or the Riemann Christoffel tensor, or you may simply say Riemann tensor. And for this, let us consider a covariant vector A mu. This A mu is a covariant vector, you know. And if you want to define the covariant derivative of this A mu with respect to an index nu, or you can say with respect to the coordinate x nu, okay, then what will be it? You have learnt already in very detail for finding the covariant derivative of vectors earlier. So you can easily say what will be the covariant derivative of A mu with respect to nu, or you can say with respect to x nu. This is denoted by this symbol, as you know, this A nu semicolon nu. It means this is covariant derivative of the covariant vector A mu with respect to nu, or you can say with respect to the coordinate x nu, okay. And you have seen earlier that this is defined as del A mu by del x nu minus this Christoffel symbol of second kind times A lambda, okay. This is just the basic definition of the covariant derivative of a covariant vector, okay. So you have seen earlier that this covariant derivative of A mu with respect to x nu is actually a covariant tensor of rank 2, okay. You have seen earlier. Now we will further differentiate this equation 1 with respect to, let us say, an arbitrary index sigma, okay. So when we will take the covariant derivative of this A mu comma nu, which is already a covariant derivative of the covariant vector A mu with respect to nu, but now I am taking the covariant derivative of this A mu comma nu with respect to sigma. So this is denoted by this symbol A mu semicolon nu semicolon sigma. It means you are talking about the covariant derivative of this fellow with respect to the coordinate x sigma. So in accordance with the definition, what you will have to do? In accordance with this definition, you can see you will have to take del x sigma, okay, and that will be operated on this tensor A mu semicolon nu, okay, and minus this much, okay, and minus this much, okay. Now actually this symbol is also written like this. This is A mu semicolon mu nu sigma, okay. Now this a mu semicolon nu, which means the covariant derivative of a mu with respect to nu. You know, this is defined like this on the basis of this equation 1, you can say. Okay. Similarly, this covariant derivative of a lambda with respect to nu, this can be written as this. Okay. And this covariant derivative a mu with respect to lambda, this is written like this. Okay. So using the basic definition of covariant derivative of a covariant vector, I have replaced all these covariant derivatives in this equation. Okay. Now let us simplify this result to some extent. When you will operate this operator del x sigma on the two quantities inside this bracket, then what will be this? This will be del 2 a mu del x sigma del x nu. Okay. And when you will operate this operator del x sigma on the second term, this Christoffel in symbol at times a lambda. This is just the product of two functions. So following the rule of differentiation of product of two functions, what you will write? When you will take this factor, that is this gamma, as a constant factor, then you have to operate the operator on the second factor a lambda. Okay. And now keep a lambda at each and operate the operator del x sigma on the Christoffel symbol. Okay. Now let us multiply the terms inside this second bracket by this Christoffel symbol. Okay. So on multiplying by this, you can write this is this much plus this much. Okay. And similarly, in the last term, we will multiply both the terms inside this bracket by this Christoffel symbol. And after multiplication, we get this result. Okay. Now, the terms in RHS, we are going to actually rearrange it in a proper form. So when you will rearrange the term, you can see that this product term, see this product term, see this product term, and in these two product terms, a alpha is a constant factor, so you can take a alpha as a common factor. Okay. And the remaining terms are at each. So when we actually rearrange the terms, then this quantity is equal to del square a mu by this much minus gamma lambda mu nu times del a lambda by del x sigma minus this much minus this much minus this much, and here in last term I have taken a lambda as a common factor. Okay. And the remaining term is like this. Okay. I am not giving the proper reading, you can see it. Okay. Now in fact now we are going to reverse the order of covariant differentiation. In fact, here we have seen that first of all we have differentiated this a mu with respect to x nu, and after that we have differentiated it with respect to x nu. So if you will now reverse the order of covariant differentiation, that is, now we are going to differentiate this a mu first with respect to sigma instead of nu, and after that we will differentiate it with respect to nu. Then what will happen? The result can be easily obtained simply by interchanging sigma and nu. When you will replace sigma by nu and nu by sigma, then the order of then the result after interchanging the order of differentiation will get readily. Okay. So you can see here I have written a mu comma sigma nu. Here there is nu sigma and you have to interchange nu and sigma. So at the place of nu I have now written sigma, at the place of sigma I have written nu. Okay. Similarly, see the first term. In this first term too, this sigma will be replaced by nu and this nu will be replaced by sigma. So this is the first term. Okay. In the second term, see here, again nu will be replaced by sigma and sigma will be replaced by nu. So the second term becomes like this. In the third term, again we will do the same algebra and the third term now becomes like this. So in the similar manner, in each and every term, nu and sigma will get interchanged, and after that you get this equation 3. Okay. Now you have studied the Christoffel symbol in my earlier lecture, and you have seen that this Christoffel symbol is actually symmetric in terms of its covariant indices. So if you will use the symmetry property of Christoffel symbol, then you can say that this gamma lambda mu nu is equal to gamma lambda nu mu. Okay. And again you have definitely a proper idea of partial differentiation, and you know, in case of partial differentiation, if our function is an exact differential, then the second order partial derivative is independent of the order of differentiation. Okay. So in this condition you can say that this term which I am crossing here and this term both will be equal. Here only the order of differentiation is reversed, but as in case of partial differentiation of second order, the order of differentiation does not matter. Okay. So this will be also kept in our mind here. So you can say that this quantity is equal to this. Okay. So keeping these two facts in our mind, that is the second order partial derivative are independent of the order of differentiation, and the Christoffel symbol are symmetric with respect to its covariant indices. When we will keep these two facts in our mind and utilizing these two ideas, when you will subtract this equation 3 from equation 2, what will be your result? You can see the first term in equation 2 and first term in equation 3 will get cancelled. So this second order partial derivative will get cancelled. So after subtracting equation 3 from 2, our result will be this minus this, and that is equal to, you can check the expressions, and then the algebra is simple, you have to only subtract. So here a lambda will be now a common factor, and there will be del x nu operated on this Christoffel symbol minus the partial derivative of this Christoffel symbol with respect to x sigma, and plus a alpha times this Christoffel symbol times this Christoffel symbol minus this Christoffel symbol times this Christoffel symbol. Okay. Now we are again going to see a simple algebra. Now we will simply interchange the dummy indices alpha and lambda in the last two terms. Okay. Last two terms, in this term and this term, we will simply interchange alpha and lambda. It means at the place of alpha, now we will write lambda, and at the place of lambda, now we will write alpha. But you know, in that condition, since these are dummy indices, so result will remain unchanged. So now you can see this this quantity will be what? Here there is a lambda times del a lambda, and here is a alpha, but you will replace this a alpha by a lambda. So now a lambda can be taken as a common factor. Okay. And this partial derivative of this Christoffel symbol here, gamma lambda mu sigma. Okay. this partial operator is operated on it, and minus this much. So this term is at ease. Okay, but in the last two terms I have told you, you have to interchange the dummy indices, that is alpha will be replaced by lambda and lambda will be replaced by alpha. So alpha and lambda will be replaced by one another. So see here, there is superscript lambda. So now we will write alpha, you can see, and here there is mu sigma, so mu sigma will be at each. Okay, and here there is alpha in second Christoffel symbol, so that will be replaced by lambda. Okay, so after replacing alpha by lambda and lambda by alpha, the last two term is like this. Okay, so now we have obtained the value of the difference of these two tensors here in this equation 5. Okay, now actually this quantity inside this square bracket in equation 5, that is written as r superscript lambda subscript mu nu sigma. Okay, this is written like this. So you can easily say that this r is what? Actually this tensor r is equal to this much. This is the bracketed terms in this equation 5. Okay, in fact this quantity r defined in this equation A is called Riemann tensor. This is called Riemann tensor. Okay, or you have seen that it is also known as Riemann Christoffel tensor or curvature tensor. Okay, and you can see that actually it is a tensor of rank 4. The contravariant index is lambda and the covariant index is mu nu sigma. So this is a 1,3 type tensor. Okay, a mixed tensor of 1,3 type, and its contravariant rank is 1 and covariant rank is 3. Okay, so it is a tensor of rank 4. Okay, now as I have told you in the beginning of my lecture, that when you will see this definition of the Riemann tensor, what you are seeing here, actually when we define this Riemann tensor R, then you can see the expression. In this expression there is either the partial derivative of Christoffel symbol. In the first two terms there is actually partial derivative of Christoffel symbol, or the product of the Christoffel symbols. And when you have actually studied Christoffel symbol, then you have seen in the definition of Christoffel symbol, ultimately there is either the fundamental tensor or the partial derivative of fundamental tensor. Okay, so in this condition you can say that ultimately this R depends on the fundamental tensor, or R is simply the fundamental tensor. So I have mentioned here, you can see that it is clear from equation A that Riemann tensor contains only the Christoffel symbols. These are the Christoffel symbols and their derivatives. See the derivative. First two terms are derivatives of Christoffel symbol. And these Christoffel symbol in turn contain fundamental tensors. Remember the definition of this Christoffel symbol. Okay, and their partial derivatives. So the Riemann tensor also belongs to the class of fundamental tensor. Okay, now we will this is the defining equation of Christoffel symbol, so you must remember it. This is the defining equation. How we define the Riemann tensor or the Riemann Christoffel symbol tensor or the curvature tensor, you have to remember this. Okay, this is actually the definition, so we must remember this definition. Okay, this is definition of Riemann Christoffel tensor. Okay. Now we will see the two important properties of this curvature tensor. First property is called asymmetric property. Actually, this Riemann tensor is antisymmetric with respect to these two covariant indices nu and sigma. Antisymmetric means this r lambda mu nu sigma is equal to minus r lambda mu sigma nu. You can see here this nu sigma and has been interchanged. This is sigma nu. So this is not a symmetric tensor, but it is antisymmetric with respect to the indices nu and sigma. Okay. In fact, if your aim is to understand this fact, this property, you can easily prove it. For this, we will simply interchange the indices nu and sigma in this equation A. Where there is nu, we will now write sigma, and where there is sigma, we will write now nu. So when you will do it, see the expression, then the Riemann tensor is now R superscript lambda subscript mu sigma nu. Originally this was nu sigma, now I am writing sigma nu. Okay. So in each term, nu and sigma will be interchanged. So the first term will be like this, second term is this, third term is this, and fourth term is this. Now let us take this minus 1 as a common factor. So the sign of each term inside this square bracket will get changed, just reversed. So after taking minus as a common factor, our result will be del x nu operated on this Christoffel symbol minus del x sigma operated on this Christoffel symbol, plus this much and minus this much. But see the defining equation of this Riemann tensor, which you can see in this equation A. So the expression inside this square bracket is nothing. This is simply the Riemann tensor R lambda mu nu sigma. So we can easily say that this R lambda mu sigma nu is equal to minus R lambda mu nu sigma. And you must remember this property because such questions will be asked in your objective type problem, and so you must remember it. Okay. Now the another very important property of this Riemann tensor is its cyclic property. Actually, when you will add these three Riemann tensors, here you can see actually the indices mu nu sigma has been actually interchanged, or you can say that the mu nu sigma indices have been permuted, okay, in cyclic order, and after that we add all those Riemann tensors, then result is equal to 0. I have not actually written the proof here. I have just given you a hint that this result can be easily proved or readily proved by permuting the indices mu nu sigma in cyclic order and adding. So you will have to obtain this. This is already defined in equation A. On the basis of equation A, now you will have to find the value of this much. Okay, and for this what you will do, at the place of mu you have to write nu. Okay, and at the place of at the place of mu you have to write nu. At the place of sigma you will have to write nu. At the place of nu you will have to sigma, and at the place of sigma you will have write to mu. Similarly, in the third term, at the place of mu, now you will write sigma. At the place of nu, you will write mu, and at the place of sigma, you will write nu. And after that, you will add all those three expressions. Then you will easily see that this becomes 0. So this property is called cyclic property. Okay. So this is all about the uh, derivation of this Riemann tensor. But as I have told you that this tensor is very important, or it is a very strong mathematical tool to study general relativity particularly. So if you want to physically interpret this tensor, you can say that Riemann tensor determines how free falling particles deviates, uh, which is known as geodesic deviation. This fact we will discuss while studying the general relativity in our forthcoming lecture. In fact, if you are talking about this tensor in special relativity, you know, in special relativity, the space-time is flat, and in case of flat space-time, or in case of special relativity, all components of Riemann tensor vanish. Okay? So this tensor actually indicates the not does not indicate the flat space-time, but it indicates the curved space-time, which is the subject matter of general relativity. So in curved space-time, you can, for example, you can say when we talk about the space-time around the stars or black holes, this tensor describes the tidal forces experienced by matter. All these facts will be discussed in terms of this Riemann tensor when we will discuss the proper theory of general relativity. Okay, so I think definitely you have enjoyed this lecture, and as always, I told you that when you watch my video, keep your pen open and notebook also open, and write down all these things in your notebook and revise it after watching the video. Everything then will be crystal clear to you. Okay, thank you very much.